Hi, everybody. It's a makeup lecture for May 13th, where my draw program crashed and I forgot to record. So it will be very similar to that lecture, but not exactly the same, although I should cover all the same material. I start by sharing my screen. Sorry, I got to get rid of the controls. Okay. So one of the major goals of neuroscience is to understand how synaptic plasticity shapes learning. And we also often phrase that as, establish some kind of link between the synaptic plasticity rules used in the brain and how animals, and animals includes humans, learn. The problem, of course, is we don't really know the synaptic plasticity rules, okay? We know a lot about pre-post rules, remember STDP from several lectures ago, but we don't really know that role of the error signal. And because of that, we don't know how the brain solves the so-called credit assignment problem. Common phrase in deep learning. The credit assignment problem basically says, given some feedback, which synapses should be updated and by how much. And that matters a lot. If you reach in your hand, let's say, reach into an oven and burn your hand, you should adjust your weights in one way. If you reach into an oven and don't burn your hand, you should adjust them in a different way. And exactly how that error signal is fed back is, except for reinforcement learning, is really not known. Okay, so what do we do? Given that we don't actually know their learning roles, we study learning roles in the abstract, okay? Basically, we make up reasonable learning roles and study them, and the goal is to gain intuition into how learning is done in the kind of large networks we see in the brain. And once we gain intuition, we'll put that to use when the experimentalists tell us, what the real learning rules are, okay? So when the learning rules come along, we should be experts in this. So the outline for the next couple lectures is, today I'll talk about unsupervised learning. I'll tell you what that is in a second. I'll start talking about supervised learning, but only barely. I'll define what it is and then say a few words about linear regression. In later lectures, we'll talk about deep feed-forward networks, recurrent networks, transformers, and then reinforcement learning. Okay. So what's unsupervised learning? It's all about extracting structure from data. Okay. And abstractly, data is a collection of vectors. It's x mu equals 1 to p. We're always going to use p as the number of training examples. So in this example, in example 1, data basically comes from a correlated Gaussian distribution, or correlated maybe approximately Gaussian distribution. So you would describe it as let's say the mean and covariance of the Gaussian. Example 2, much more complicated. It comes from a mixture of distributions. I wrote it as a mixture of Gaussians, as is often the model, but it could be a mixture of anything. Okay, so just looking at that data, you can see the structure. It's actually quite easy. The problem is that in most of the time, or first of all, it can be much more complicated. It can be like this. So you have some sort of complicated distribution, which is hard to describe. Oops, I do not know what's going on. Okay, I'll get rid of this later. So in 2D, it's kind of easy to visualize the data. Realistic data is high dimensional. Okay, live in easily in 10 or 100 or 1,000 or 10,000 dimensions. So visualization doesn't necessarily help. And so what we do is instead is build a parameterized model. Say what that is in a second, and estimate parameters. And I'm going to start with a really, really simple model that's motivated by neuroscience, as we'll see. But it can be used to fit a certain kind of data. And the data that we're interested in is the data lies more or less on a line. Okay, so the data points are down here. It's more or less just they lie more or less on a line. We want to find the direction of that line. So what we do, so again, we have p data points. We're going to actually let p get very large. It can go to respectively go to infinity. And we're going to model it as y equals w dot x. Okay, and what we're interested in is this w. And we kind of make up a learning rule. So the change in the weight vector is for sample mu, it's y mu times x mu. Remember, y mu, we don't know y mu, we just model as w dot x mu. And so to see that this is actually what we call a Hebb rule. If we think of activity y as being connected to a bunch of presynaptic neurons, and y is a linear model, sum on I of wi(xi), that's this term here. So y is actually the postsynaptic. So you could build a neuron like this without knowing anything about y. We just model it with x. X is the input. Y is the postsynaptic signal. X is the presynaptic signal. So our learning rule is really, we can think of our learning rule for each synapse as delta wi equals eta times y mu x mu I. The ith component of the vector x mu. Okay, so it's just basically it's that synapse gets updated. This one here gets updated by this relatively simple rule. So in some sense, this model was motivated more by neuroscience than by unsupervised learning, but it is technically an unsupervised learning algorithm because it depends only on the data and no real training signal. So what we want to do is analyze this data and see, is it really the case that W lines up with the sort of the long direction of the data? So here's our model. So remember this term here. Oops. So W dot x mu. This is just y mu. All right. This is y mu. So it's the same. It's a usual learning room. Eta y mu x mu. That's for one example. But what if we have p examples? Basically, we just sum up every time we get a new training example. We just sum them up, so we get the sum on p. And we're going to divide by p. That's this term. And multiply by p. We haven't done anything there. But this term here is basically an estimate of the covariance matrix, which is exact when p goes to 0. So if you have enough training examples, we're going to just replace this thing by the true covariance matrix. Okay, and if p is really large, that's fine. Okay, and therefore our learning rule, if we call eta times p, we call this delta p. We divide by delta p, and we get a learning rule that looks like this. Uh-oh. And then we let delta t go to 0, and we just get an ODE. Okay, a differential equation for the weights in terms of the weights. Unfortunately, it's a linear differential equation, which we know how to solve. And the way we solve it is use the eigenvectors and eigenvalues of sigma. Okay, whenever you have linear equations in more than one dimensions, eigenvectors and eigenvalues tell you everything. The eigenvectors and eigenvalues are defined by this equation. Hopefully you've seen that before. If not, it's going to be a bit mysterious. Sigma dot vk equals lambda k vk. And these things are orthogonal. Vk dot vl is the Kronecker delta if it's 1 if k equals L and 0 if k is not equal to L. Which we're not exactly going to use, although we kind of do. Okay, so how do we use eigenvectors and eigenvalues to help us solve this equation? We actually expand the weights in terms of the eigenvectors. Eigenvectors actually form a complete basis. So W lives somewhere and is some combination of these eigenvectors. And that's nice because sigma dot W is basically we take W, we stick it in there, and we get a k of t times sigma dot vk, the eigenvector. Okay, and the sigma dot vk, it just brings out a factor of lambda k from here. Okay. Once again, I do not know why that's there. So our equation becomes dw dt is d dt of the sum on k of ak bk. We bring the d dt inside, dak dt and then what we see is that actually we use something small. We use this term here is the same as that term there. Okay, so our equation becomes dak dt equals lambda k. And that's a one-dimensional linear differential equation. We can immediately write down the solution. It's basically ak of t is ak of 0 to the lambda. Okay, so we've written wk in terms of ak bk, and we have explicit expression for ak. It's ak of 0 e to the lambda kt. And so this is exponential growth. We'll assume all the eigenvalues are different. So in the long time limit, only one of these survives. Okay, the one with the largest growth. So lambda k star, we'll assume it's a unique largest eigenvalue. And so what that means is if you have some data like this, this is V1 right here, okay, and this is V2. These are two different vectors, or the eigenvectors of covariance matrix. Again, I don't know why it does that. And it eventually picks out the largest one. So in a situation like this, eventually W, sorry, there it went away. Eventually W would point in this direction. Okay, so this it does as advertised, right? So this really this very simple learning rule finds basically the largest variance direction in the data. Okay, now it's not a great rule because of this, right? W goes to infinity, so it's completely unrealistic in that respect. That can be fixed by something called Oh's rule, where you subtract off this term. It's not hard to show that in that case, W converges again to the eigenvector of sigma with the largest eigenvalue, but now it's finite. Okay. But now W is, but in addition, W is finite. Okay. So it doesn't go to infinity, it's just pick up the right direction. It picks up the largest, what's called principal component of the data. You can augment it if you want. So that it picks out other principal components if you want. But it's, you know, and it's not, so in that case, it's kind of a nice learning rule. But remember, it was pretty much made up. Okay, we just made up a learning rule. What we really want is a more principled approach. Okay, and the more principled approaches use parameterized models. So as usual, we have data. This is our data. And we model the data as a probabilistic model with a parameterized probability distribution. So P theta of X. So theta is a bunch of parameters. It can be one, it can be lots. And we choose those parameterized to maximize the log probability of the data. Okay, so typically we put 1 over p here just for normalization. We want to choose the parameters so that basically the data is relatively likely under those parameters. To see how this works, I'll pick a Gaussian. So in this case, theta are vector parameters. There are 2 of them. There's a mean, m, and a variance, sigma squared. Okay, we can't use mu for mean, we have to use it for something else. So our probability distribution, p theta of x, is just a standard old Gaussian. And when we take the log of that, it's kind of nice. We get 3 terms, minus 1 f x minus m squared over sigma squared. That's a data-dependent term. We have subtracted off minus 1 half log sigma squared for the normalizer. And that's relatively important, as we'll see. And then we just have a constant, which we can end up ignoring. Okay. Now, when we plug in the data, okay, the log probability, we just sum over mu. It's just this term, right? That's the only data-dependent term. And then these 2 constants go along for the ride. Now, if we maximize this, it's quite easy to show that if you differentiate with respect to m and set that to 0, you get m hat is the mean. If you differentiate with respect to sigma squared, you get the usual expression for sigma squared. Okay. And these are this is exactly what you want. It's a standard expression for the mean and the variance. Okay. So this is kind of nice, right? We say, okay, I'm going to assume the data is Gaussian, and it just spits out the mean and variance of Gaussians. But that's not a very powerful distribution. A more complicated example might be a mixture of Gaussians. So with different these Gaussians come with different probabilities. Each of them has a different mean and variance, and then different probabilities. And that would be a good model if your data looks something like this. You know, a bunch of data points here and here and here, but they're spread out. Clearly not a Gaussian, but not an easy distribution either. Multimodal. And you have now sort of a bunch of parameters. First of all, k is the parameter. You don't know ahead of time how many mixtures you're going to have. And so you have to learn the number of mixtures, the mean of each one, and the standard deviation. And of course, this can work in high dimensions if you want. The mean can be a mean in high dimensions, and you can learn the covariance matrix instead of just the covariance. Okay. Now, in this case, in the Gaussian, single Gaussian case, we could do things analytically. There are no closed form expressions. Okay. You have to use approximate methods like expectation maximization. Machine learning, I spend a lot of time working things out. Sometimes they work, sometimes they don't. And of course, there are lots of distributions you can make up. And something that's sort of more interpretable, but in some sense it's exactly the same model. And these are actually probably the best and in some sense most popular model are latent variable models. So latent variable models, you model the data as there's some latent z, and the data condition on z, you have some distribution. So p theta might be relatively simple. Sometimes it is, sometimes it isn't. But you now model 2 distributions. Again, there are no closed form examples. And what I mean by latent variable, it's something that typically is interpretable and generates a data. So if x, for instance, were pixels in an image, z would be objects in the world: cows, trees, houses, people, cars, dogs, cats, whatever. I mean, it can be all sorts of things. It can include textures, all sorts of things that appear in the world. And given the set of objects in the world, that generates the pixels. Again, no closed form expressions. You have to use approximate methods. And often, both of these distributions are parameterized by deep networks because you need relatively complicated distributions to describe real-world data. And finally, there are contrastive methods, which are becoming more and more popular. But and these are actually only sort of weakly supervised. Your data goes through a deep network, and out comes y. Y could be a label, or it could be anything. It's abstract, right? This is so that could be a label. It could be multidimensional. It doesn't matter. And the only loss is that similar inputs should produce similar outputs. And different inputs should produce different outputs. So a loss might look like something like this. So here's a difference between two inputs. In this case, you have to put in two inputs at a time, generally one after the other. And the loss is, and this is the difference between the outputs. So if x1 is close to x2, y1 should be close to y2. If x1 and x2 are far apart, y1 and y2 are far apart. And these now actually, after years and years of sort of fine-tuning them, they work pretty well. And they're possibly a good model of what the brain does. In fact, they even made a baby cam where they put a camcorder on a baby's head, let it wander around for a couple of years, trained on that, and they did an okay with the model. And they trained it actually completely unsupervised way. They sort of used time as a proxy for how close things were, and they actually did a pretty good job training a visual system. And they're now going to up that to include audio, and it's kind of a cool approach. Okay, so that was unsupervised learning. It's a field that's not as well developed as supervised learning, but it's probably more important. Technically, everything you learn is unsupervised. If you do count a supervised signal, it's very sparse. So your mom tells you, look both ways when you cross the streets. You learn things in school, but most of what you learn is unsupervised. You observe the world and you observe regularities, and you learn those regularities. Okay. The reason we talk about supervised learning really is because it's much more developed. Okay, and it can give you a little intuition into how learning works. So now instead of having only x mu, we have x mu and y mu. Okay, we have an input and an output. So image, for instance, in terms of vision, input might be images and the output might be labels. This is a car, it's an airplane, it's a tree. And you have to learn the mapping from images to outputs, okay? And abstractly, we're going to see some explicit forms for the function f, but we write it as f of y equals f of w, a set of weights, that could be a large number, and x. So this is a parameterized nonlinear function. We want to minimize the loss, called the E for empirical loss. So this is a loss you can get just on your data set. Okay. So 3 comments. The first is kind of a minor point. Other loss functions are possible. And often for labels, square loss doesn't make sense. Instead, you use actually Kullback-Leibler divergence. Instead of having the output being y, the output is actually the probability that x has label k. And k might be dog, cat, tree, it could be your set of labels. And so the network spits out a probability, which is kind of reasonable, right? In some cases, it should be more sure than others, so it's kind of nice to have probabilities. And the loss is the KL divergence between the true distribution, pk star, and the distribution learned by the network. Okay? pk star is especially simple because the true probability is either 1 or 0. So you can replace this whole sum by basically minus log of pk star. This is k star, so you only have to look at 1k. So basically what it does is try to make the probability, the correct probability as large as possible on every trial. This is called the log loss. Okay, and and you can actually tweak this, but it's very intuitive, loss for labels. We won't be using it much, but just to let you know that square loss is not the only loss function one can use. Now, the other comment is, remember we optimize the training error, right? We optimize the error on our training example. What we actually care about is generalization error. And generalization error is the true loss is if you averaged over all the data. If you had basically an infinite number of training examples, this is what we want to minimize. And whether or not, so remember, all we can do is make the training error small. That's the only thing we have our only option. And whether or not small training error implies small test error depends on the architecture and the number of training examples. Okay. And in some sense, all the advances that have been made in deep learning in the last, well, in the last 100 years, in the last 50 years, actually, since it was invented, people look at different architectures and they have more training examples. And that's all. Conceptually, I would say there have been no advances whatsoever. And finally, we're interested in over-parameterized networks. Okay? Number of weights is n, number of training examples is p. We're going to use n and p consistently in the rest of the lectures. And over-parameterized means n is bigger than p, and sometimes n is much bigger than p. And that's the regime that's actually highly relevant for the brain. Okay? Let's just count parameters. So we know n. There are 100 trillion weights, 100 trillion synapses. So n is 10 to the 14th. Let's assume you had one training example per second. Okay? And 16-hour training examples per day. There are 30 million seconds in a year. So that means 20 million training examples per year. This is 1 billion training examples in 50 years. 1 billion is 10 to the 9th versus 10 to the 14 weights. So P over N is tiny. It's 10 to the minus 5th. Okay. That's also, so it's not that small in deep networks, but typical modern deep networks, P over N is, somewhere between 1 over 10 and 1 over. So you have 10 to 100 times more free parameters than you do weights, which is not supposed to work. One of the mysteries about deep learning is why it works, and we'll kind of demystify that in the next couple lectures. Okay. I'm going to start with linear regression. This is actually going to be my last slide because and we'll continue with linear regression in the next lecture. So linear regression is basically a shallow network. It's one of the best to understand networks in the world, which is why we look at it. And it actually does have relevance for deep networks, as we'll see. So y is w dot x, which is just a sum on I of w I xi. We'll consider a student-teacher setting where y star is w star dot x is a true model. We won't consider noise, but it's not hard to consider. And remember, we have training examples x mu, y mu. We have t of them, p of them. And the kind of strange thing, we have n parameters, right? In this model, and you would think you want p greater than n. That would be your sort of first guess, right? You have n training examples. You have n unknown parameters with only p training examples. How can we learn them? It turns out you can't. So the idea is that you need p greater than n is completely wrong, and we'll see why in the next the next lecture we'll see why. Okay, and that'll give insight into why deep networks can learn even when they're massively over-parameterized. Okay. That was it. I go a lot faster when I preview the slides, which is fine online. Okay, so this lecture will appear. Well, by the time you see this, it will be. Okay, thank you.